Hi, everyone, and welcome to this session on emerging optimization problems and algorithms. My name is Ali. I haven't heard the introduction, probably because there was some echo in the background, so they had to mute the microphone. So thanks for letting me know. I'm based in Brisbane, Australia, and leading our research center at Torrens University, Australia. So today I'm going to be talking about optimization problems emerging, I should say, optimization problems and algorithms. And here's the outline of my talk. I'm going to start with the problem and then focus on the algorithm. And that's because I tend to look at the whole field of optimization through the lens of problem, because an algorithm by itself doesn't add any value to, doesn't add any value. It's the problem that, gives a spirit to an algorithm. And often people, when they approach us, the first question they ask is about the algorithm. What's emerging? What's the best algorithm in 2022? Whatever. And that's not the right question to me, because if anyone asks me what's the best algorithm, I can't answer that question because we need to know the problem. And the analogy that I always use is a lock and key. Let me just use this laser pointer. So if you are locked out of your house, right, you don't just ring your or call your keysmith or your friend to ask them for a key. Obviously, you need to know what type of lock your door has, and also, bring some expert to open it for you. Sometimes they can build or customize a key for you. Sometimes they have some master keys that open a lot of doors or a lot of locks for you, right? So all I'm trying to say is that it's a good practice. It's a good habit to look at the whole field of optimization through the lens of problem. And this is the problem that gives meaning to the whole community. I'll probably spend 15 to 20 minutes, more or less, on optimization problems. I'll be focusing on the main components of any optimization problem, from small to big. It doesn't matter how complicated or how complex. And then I'll focus on algorithm. And I'll answer an important question that people ask us recently: why a lot of algorithm tends to be nature inspired, why people look into nature to develop algorithm, why not artificially made. Those are the several questions that I will answer towards then. So with that being said, let's get started with optimization problems. Any optimization problems, which I'm going to use now the term system, because it can be a business, it can be a process in a business that you're trying to optimize. It can be, the whole organization KPI, for example, revenue or operational cost, and so on and so forth, that you're trying to optimize. So let's call it a system that you're trying to optimize. You have a set of inputs, what are often referred as variables, decision variables, arguments, parameters. I tend to use the term input because those are the unknowns that we provide the system with, and we don't know the best values for these. The whole goal is to find the best values for those inputs to be able to maximize or minimize the output, right? And the output is what the system produce, what we often call cost function, fitness function, merit function, and so on and so forth, right? So the goal is to find the best values to minimize or maximize this output. But there is another component called constraints. Constraints allow us to bring decision makers' preferences. For example, if you're trying to design a table, a rectangular, a square-shaped table, or rectangular table, I should say, by saying width should be equal to height, you can, by adding that constraint, you can filter out a lot of undesirable input. So the very first step, I haven't been given any background about the audience, but I assume we have a lot of engineers on this call, and also computer scientists. So one of the key things I ask everyone, whether you have a problem, you want to solve it, optimize it, or whether you are a computer scientist and do research in optimization or algorithm development and so on and so forth, the very first thing you want to do when it comes to solving a problem is to identify those three components. It's quite important to properly and accurately identify those, because if you do not, because that will help you to then do what? To formulate that problem. If you get the formulation wrong or inaccurate, if your formulation is inaccurate representation of what you're trying to solve, you will definitely end up finding, you know, undesirable solution, even if you employ the best optimization algorithm on this planet, right? So again, very important. So I always get people to grab a piece of paper, draw a table with 3 columns, 1 input, 1 output, 1 constraint. And even if even they give me some narrative, some paragraphs, then I can extract what they are trying to achieve and the components of the problem from that. So anyway, as you can see, I have, without the loss of generality, I assume we are trying to minimize f, which is a function of those inputs, subject to not violating the constraints, right? And after doing that, this is where an algorithm comes into the mix, right? So it is usually sitting outside the system as an outsider, trying to tune those parameters to be able to maximize and minimize the input while listening and considering those constraints. Sometimes the optimizer or optimization algorithm consider the system as a black box. Sometimes it is a gray box, which means we need to know a little bit about, or an algorithm needs to know a little bit about the internal mechanism of the system. All right, so I mean, I'll show you a very basic example, to be honest, that can be generalized to a wide range of problems. What are the challenges that we face? I'm going to be using some technical terms, which I'll discuss in a moment. What do we call search space or search landscape, right? So if you assume that little guy, the robot, is trying to, you know, navigate on this mountainous region, on these peaks and valleys, to be able to find the minimum. Let's say if this is the energy function, energy of a system, and you are trying to find the best values for X and Y to be able to minimize. Obviously, the best solution is one of these. I can't tell exactly looking at the heat map, but definitely it's one of these two. That one is also not bad. But yeah, so real world problem do not come easy. Some of the challenges that we have, I'm going to discuss in a moment in the next few slides. But just looking at this, as you can see, there are so many peaks and valleys that you have to avoid. There are so many gaps that that are created by constraints that you have to avoid. And usually a lot of real world problems have a lot of variables. You're looking at the problem with 2 variables and 1 objective, 1 cost function, let's say energy function, whatever. But usually you have a lot more, which means visualization will become difficult. And obviously, the more variable you have, the more difficult your problem will be. So before I dive into some of the complexity that people deal with, and if you're a postdoc or if you're a PhD student, or if you have a PhD student at the beginning of their candidature, it will give you some direction, you know, so they can land on the cutting edge research gap or cutting edge technology and understand the research gap. So how do we work with people when it comes to solving an optimization problem? It is a cycle. It is an iterative process. So what happens is that often people come to us and it begins with discussion between what we call problem owner or decision maker, what you can call somebody who owns the problem, who wants to solve that problem, and us as optimization expert, okay? We will sit with them to formulate the problem, usually, and often, we are the one who help them to do that problem formulation, right? Not in terms of, you know, programming, not in terms of mathematical equation, no, just identifying those even components are quite important. Then what happens, we take the problem and go away and start doing some experiment. This is where we probably try different variants of the problem, try different algorithm, try different statistical techniques to ensure that the solution that we found is reasonably good. We take the solution back to the problem owners. If they are happy, well, everybody will be happy. Obviously, we'll get our final check or approval, and that's the end of the project. But honestly, usually it's a lot of iterations that we have to go through to ensure that the problem is properly formulated and the solution that we found is optimal and is good enough for the decision makers and problem owners, right? So it is a cycle, and probably that reminded, for those who are software developers, probably that reminded you of, you know, agile or iterative software development life cycle. So, and I tend to agree with that in optimization as well. You don't want to spend all of your time on, you know, formulating the whole problem. You can sometimes start with a sub-problem and build from there while decision makers are, making their mind. So what are some of the challenges that people face when it comes to all of those components: inputs, constraints, and outputs? When it comes to inputs, usually real-world problems have a large number of decision variables, and obviously the more variables you have, the larger the size of the search space and the more difficult to solve, right? If that's the challenge that you're dealing with, most of the optimization problems may struggle when it comes to solving these types of problems. There is a specific field of study called large risk optimization, in which people develop, techniques to address those. So if that's a challenge you are dealing with, you should be looking at that sort of, literature. Variables may have different ranges. It's not the case that always, you have the same range. There are different ranges. Some of the inputs may be dependent, right? And that means it's quite similar to feature selection in machine learning, right? Some of the features might be redundant. Some of the features might be highly correlated, which means you can, simplify them into one or two or smaller set. This is exactly what happens in optimization as well. When you're dealing with a real-world problem, sometimes you have thousands of parameters to work with, but not all of them should be optimized. Some can be calculated based on others. Some can be simplified looking at others and things like that. So again, that's a sort of complexity that people deal with. And sometimes we have discrete variables in which we are dealing with. We are not dealing with continuous variables. It's a set of discrete values that you have to find optimal solution for. Sometimes you have mixed integer variables, which is what we need, but definitely need to be addressed. And last ones, which is quite common in real world problem, is where you have noises in the input, which means usually we use simulators to calculate the output of the system. And when we find the optimal solution for those parameters, the manufacturers will build the product, or they achieve the outcome with some sort of errors. This is where things can be changed in the final product, right? So considering the inputs, noises in the input during the optimization process is what we call robust optimization, right? Robust optimization allows you to minimize the impact of noises. And noises can be also applied to objective functions too. So if that's the sort of challenge you deal with, you should be looking at the literature of robust optimization. Challenges in the constraints, right? Some problems are highly constraints sometimes, and that means you are dealing with, and that's usually the case in real world problem. And that's the case in which you need to, and you are dealing with highly a search space that is heavily dominated with the invisible region. And that means every solution you find is violating a constraint to some extent and of any sort. So for those problems, probably you need to come up with mechanisms. Like we had a case in which we had to feed the algorithm with some solution to start with, let alone to convert to something. Constraints are categorized into equality and inequality constraints. And obviously equality constraints are much harder to deal with. And some constraints are not as important as others, so we can prioritize them, which is the term what we often call soft versus hard constraints. That means soft constraints can be violated slightly, and that is defined by obviously the nature of the problem, but some constraints are really hard, so you do not have to violate them at any cost, at any degree. And finally, what are some of the challenges in the output? Often real-world problems have more than one objective to optimize, and this means you are dealing with now multiple of those mountainous regions that I showed you earlier, right? You don't have one of them; you have multiple of them. Those objectives might be in conflict. That means you're trying to improve one, the other one, you're trying to maximize one, the other is minimized, assuming the fact that the second one should be maximized. So obviously, you need to find mechanisms to address those. Sometimes you can merge the objective into one objective in which you need some sort of decision makers' preferences and some sort of decision making in the process. but sometimes you can maintain the multi-object formulation and find the Pareto optimal front, which I'm not going to get into the details unless there is any question later on. So some problems may have dynamic objectives, and that means the search space changes over time. If you think about it, a lot of path planning, robot navigation, self-driving, a lot of systems that are relying on images and videos are indeed dynamic. Not always, it's not, I mean, that's one example. So that means time also matters. That means what you're trying to optimize changes over time too, right? So that means you have to keep checking the reliability of solution and ensure that it changes, it stays optimal over time. So dynamic optimization is what people tend to use in those kind of problem areas. And that's pretty much everything I wanted to cover. It's a time to have a look at the classification now, right? So we can classify an optimization problem, which is everywhere, obviously, I'll talk about it in a moment, based on formulation. I've just taken you through these, like single objective, multi-objective problems that are constraints on constraints, a wide range of constraints. Or you can categorize them based on the characteristic of the problem. Some problem changes over time, what we discussed just now. Some problem have linear search space, search landscape. Some are non-linear. Some are unimodal. Some are very multimodal. Some are convex and non-convex. So, as I said, going back to the framework that I gave you earlier, so what we tend to do at this stage is to understand where the problem is sitting, what sort of characteristic the problem has. And once we do that, then what the next step is to start solving and optimizing the problem. So there's a bit of, and before I go to the next part of my talk, which is about optimization algorithm, there's a little bit of personal story behind, what I've described just now, right? I think it was 20-sometime years ago, I was sitting in a lab for the first time trying to optimize a problem. And I'm a very visual person. You might have noticed if you come across my papers or my team papers, or if you have noticed already in this slide, right? So I decided to visualize and see what am I trying to do when I solve that problem. I can't exactly remember what problem was that. Probably was a logistic problem, supply chain optimization, things like that. But I tried to visualize it, and I ended up having, it was multidimensional, but I ended up having these small little, search spaces. And I thought, okay, so this is what we are dealing around the world, right? Everything you look at, from massive bridges and skyscraper to small things like path planning and, all these small, manufacturing problems, people are trying to optimize those little search spaces. And that made me think, okay, so how do we people then solve this? How do we ensure that, the optimality is there? That led me to, that was the beginning of my whole career, I think, on optimization algorithms, right? Obviously, as a beginner, the first algorithm I came across was gradient descent. And probably if you do a bit of literature review, the first thing you come across is gradient descent. We know that if we can calculate the derivative of problem equations, right, and you follow the gradient, it takes you to a locally optimal maxima, and if you follow the negative of that, it will lead you to a locally minimal or locally minimal solution, right? And there are some issues in this kind of obvious algorithm. I'm not going to talk about it at this stage, but they are still relevant. I mean, if your problem is, not highly multimodal, if you come up with proper mechanisms, you can calculate the derivative of your problem, you can definitely still use this algorithm. And it is still a relevant algorithm in some communities, like deep learning community, machine learning community, still do use these kind of algorithm. Although I'm sure you agree with me, there have been so many variants of some sort in the literature, and all they are trying to do is to, tackle several issues with, this sort of algorithm. One is the fact that they get stuck in locally optimal solutions. So some of the algorithm will tend to diverge and then converge back to wherever the global optima is, or the local optima. Some are slower, some are faster. Even when it comes to these kind of saddle point in which you have gradients at different, directions, some really get stuck. So this is even harder than a locally optimal solution. But some ADA or ADAM, which you might have heard of from the deep learning community, are indeed quite, popular on those problem areas, which is what we call obviously training neural network or deep learning model. But the challenge is there. And for those who have used these algorithms, you know that they tend to struggle when you apply them to engineering problems, right? First of all, it's a lot difficult to calculate derivative of the search space. And also, they are not designed to cater those kind of complicated search spaces. Like as a test, you can take Adam algorithm and test it on one of the engineering case studies that you are dealing with. It is slow, although it performs really well in machine learning applications, right? So choosing a proper learning, and most of these algorithm, gradient-based algorithm, they have some sort of learning rate, which can be difficult to tune, and the performance of the algorithm heavily rely on that. They are dependent on the initial position of the initial solution, and they're still, prone to locally optimal solution. They're prone to a stagnation of locally optimal solution. So. And all these, obviously, and that was the issue that I had also. I mean, that gradient descent algorithm didn't work for me because it was a local search. I needed to calculate derivative, and it was a single solution algorithm. So then it made me to think and search for other algorithm. I was looking for something that is gradient free, that allows me to extensively search a search space, because it was a very complicated problem. I needed a little bit of randomness in the search just to make sure that things do not get stuck in locally optimal solution. And I was looking for something that is robust enough, not one solution. I was looking for multiple solutions. And obviously, I came across this beautiful field of study called evolutionary computation. So I've taken you through this story to show you why we have heard a lot about, evolutionary algorithm recently, what we often refer as meta-heuristic, which is a little broader than evolutionary algorithm, but you get the idea, right? So computational intelligence is where, is the overarching field of study, which, includes obviously neural network, fuzzy logic, and evolutionary computation. So before I get into a bit of, I'm not going to get into too much of details on the, algorithm and things like that, unless if there is any question later on. But one of the questions that people often ask, why we've seen a lot of algorithms that are nature inspired. And why, does it even matter if, does it even make sense? Is it wise to look into nature and learn from it and solve problems? To me, the answer is yes, but to convince you, and I'm gonna go through a bit of theory and put my logical hat on, to understand why nature tends to solve problems in an optimal manner. I'm going to refer to a theory called emergent complexity. By definition, emergent complexity is a phenomenon whereby large entities arise through interaction among smaller or simpler entities. So there are two necessary components, right? One is we need some sort of units with simple behaviors, and those units can be physical particles, let's say water molecules or sands or even birds or ants, anything that is small, right? And not in terms of size, but a small unit with simple behaviors, right? Anything that is simple, I should say. There are some external forces that get them to cooperate. Probably cooperation is a very loose term here because they might not have any mind. There are some physical particles, but some external forces get them together to perform some sort of behaviors. What we get is some complex behavior resulting from an optimization process. That means those units, go through some optimization process to show those beautiful complex patterns. And it's around us in the world, in the nature. We have seen thousands of examples. For example, looking at the beautiful snowflakes. What are the units? The units are H2O molecules. What are the forces? It's a temperature, it's the humidity, it's the path that they travel from cloud to the earth, and based on that, they will create these beautiful crystals. What we see a lot in Middle East, small sands, go through. And the forces around them are gravity and winds and things like that, right? They will create these beautiful sand domes. So these sandoms are also the result of an optimization process, which I'm going to discuss now. And we are surrounded with thousands of other examples. And what you see is a beautiful bridge, natural bridge, a live bridge for them to navigate an environment, a flock of bears trying to minimize the drag and maneuver very, complex airflow, fish, wolves, and so on and so forth, right? So, and it's quite interesting that emergent complexity is not fundamentally natural. We can even develop artificial systems that show complex behavior. For those who know what the game of life is, with turning on and off some pixels based on some rules, you can get quite interesting behaviors, right? So we can achieve complexity. The question is, so what? Not every complex system is useful, but what about the complexity in nature? There's a very interesting reasoning behind it. So if you think about nature, let's say in billions of years, there have been two solutions to the same problem. One that is very complicated, the other that is very simple, right? Obviously, evolution tends to choose the one that is simple, simply because it consumes less energy, right? So if there is a complexity in nature, it's for good reason, and that reason is optimization, right? So all I'm trying to say is that complexity is not always good, but and not every complex is good enough to develop something. But when it comes to nature, the complexity is the result of an optimization process. So in a nutshell, evolution in algorithm and solve intelligent techniques are useful application of emergent complexity. And I have to put it out there, not every problem can be solved by looking at the nature. Not everything that happens in nature is good enough to solve our problems, right? But I hope I've been able to convince you that it is at least wise to inspire from natural systems. Number one, they are complex behavior that solve problem efficiently. A lot of problems in computer science are quite similar to problems in nature, for example, path planning, scheduling, and so on. Because we have simple unit interacting through some forces, they are really scalable without extra cost. So, and going back to the point I mentioned, a lot of problems that we deal with are indeed can be found also in nature. For example, finding an optimal path to a food source by ants in an unknown environment is similar to finding a global optimum in an unknown search space. So if we can understand how ants collaborate, simple units, forces that they get them to collaborate, we can then deploy them on our own problem to find the optimal path, right? For those who know what the traveling salesman problem is, which is a very relevant logistic problem, you can clearly see that this is trying to find the best path. Another example, migration in flock of birds in an unknown environment to minimize energy consumption is similar to flying in an unknown search space of a problem to minimize the cost function that I showed you earlier. And that is obviously the inspiration of one of the most widely used algorithms called particle optimization, which you can see some artificial birds are moving around trying to converge to certain points over the course of some iterations. So I've got 2 slides left, and I'll open the floor for some questions. So where are we heading now? I mean, if you look at the history in the last 20 or 30 years, I think I'm sure you agree with me that we've seen a lot of automation in different industries. In algorithm and computer science also, there has been a lot of automation from the programming languages all the way to algorithm and data structures and so on and so forth, right? So people used to develop heuristics, which are good for one set of problems. They are like, for example, A-star algorithm in path planning, classic AI algorithm, but not good enough to solve a wide range of problems. Then we moved into era of meta-heuristic, in which we can create a problem that uses heuristic depending on the cost function, not the problem itself, just the output of the cost function. We've seen now a lot of algorithms that are hyper-heuristic, which means they can tune themselves. They are adaptable. They're quite flexible to maneuver different types of problems. And it's keep going on. So if you think about a curve, automation is increasing over time, right? So who knows what happens? I mean, the fact that we are still using von Neumann architecture in computers, I think we're going to see this sort of automation, but definitely with other types of computing, like quantum computing, this will be changed. The whole narrative will be changed, because the way that we solve some types of problems that are difficult will be changed to, which is happening already. But what I'm saying, it will remain more mainstream and more accessible to public and to all of us as researchers. So this is my last slide. Some takeaways from this talk. Everything can be optimized, but the question is how and why. I'll show you the how by formulating the problem and choosing the right algorithm. But also I want to stress that always, one of the common mistakes that engineers tend to make is they're trying to optimize something that is absolutely unnecessary. So if you can optimize something, that doesn't always mean it's good. Sometimes the thing is to simplify that system, remove that component, and then optimize the other part. So always ask the why, not for the sake of optimization, but we have to do it for a purpose. Formulation of the problem is a stepping stone to solve it. Some complex natural behaviors can be explained in terms of emergent complexity. Emergent complexity in nature is a great source of inspiration to develop heuristic, meta-heuristic, and hyper-heuristic. We can accurately simulate these behaviors to understand them from a biological perspective and also to solve optimization problems. And that is all I have for you this evening. My time is probably afternoon Jordan time. If there is any question, I'll be happy to answer.